So, hello guys, welcome to our next video in the playlist Google Earth Engine for land cover applications. So, in our previous video, we have seen how we can build a classification model with the random forest machine learning algorithm in the Google Earth Engine. So, this is the next part of it. We are gonna uh, measure the accuracy of the model with the help of some of the statistical measures such as the Kappa coefficient, the confusion matrix. So everything will be covered in this video. So let's just start. So if you can just watch our previous video before you go to the accuracy assessment. So our tutorial 4 34 build a classification model is there. So just scroll it down to description. You will find the code link here. So just click on that. So you will get into our script which we have covered in the previous video. We have built a classification model and we have applied the same model into three regions of interest across the state of Karnataka. So now we are gonna assess the accuracy of the model with the help of some of the useful statistical measures such as the overall accuracy. So we have some problem in opening the previous script, so just go back and click on the link again. So with the help of the overall accuracy, producers accuracy, Kappa coefficient and F1 score, we are gonna assess the accuracy of the model accurately. So now we will just go through what we have done in our previous scripts. So just scroll it down. We have taken the Sentinel-2 image. We have filtered it to our latest date of 2025, and we have filtered the cloud cover also to 0.1%, and we have selected only the bands which are starting with the letter B. So these are the some useful bands, and we had also the scaling for our pre-image collection where the 0.0001 is used as a scale value for Sentinel-2 images, and we have took the median composite of our image collection and clipped it to our first region of interest. And we have added to the map with the help of map.addLayer function. We have added our uh, region of interest and the true color and false color composites to the map with it several bond combinations of B8, 4 and 3 for false color composite in order to detect the vegetation and buildups, and we have also added the true color composite with the band combination of 432 RGB, so in order to visualize the properly. So then we have created some of the training inputs in order to train the model. Uh, we had four classes in our classification model. One is the vegetation, second is the buildup, third is the barren land and water. So we have merged it into a feature collection, and we have printed it down. So as you can see, we had 382 elements in our training. We have provided 382 elements for all the classes in order to train our classification model, and we have sampled the regions with the help of this training, and we have created a variable called training features. So for my input image with the 12 bands, I have sampled the region with the use of training features, and for the property class, so at a scale of 10, that is the resolution of the Sentinel-2, and we have print the training features. So if you can just expand this, these are our training feature with 382 elements. If you can expand, we have the first feature with the properties. So here you will see we have the reflectances value for our training input for all the 12 bands, and for the class number also we have in here. So after that, we have used a classifier called Smile Random Forest, a machine learning algorithm classifier with a 500 decision trees. So you can increase this or decrease this. You can have any number of any number of trees for your Smile Random Forest algorithm. And we have trained this classifier model with our training features for the class property, and the input is our image.band names. So we had our classifier ready, and we have applied this classifier to our image with the help of the classify function, which intakes classifier as an input. So we have added this to layer, and now we have a classified region of interest 1. So let's just zoom into our first region of interest. So Just come in here and paste it. ROI 1, click on the run. So if you have multiple map.center objects, so the latest one will be considered. So please remember to have only one map.center object. So we are zooming into map.center object 1, and you can remove the zoom level, so you can automatically get zoomed into a better zoom level. So this is our classification model now, which has worked. So now we have to do the accuracy assessment type. So let's just ignore whatever we have applied as of now, so because we are calculating the accuracy for our the main model. So you just add a comment called accuracy assessment. So what the first step is that whatever the training input we have provided, we had 382 elements in our training data. We need to divide this training data into two sets. So one is used for the training the model, another one is used for testing the model. So if you can just split it down, it would be helpful. So you create a variable called GCP. So it stands for the ground control points. So I have my training, which is my original input training in order to train my model, and I'm gonna have one function called random column. So here we have this random column. So just check the documentation of random column. You will get ee.feature collection the random column. So just open it. You will see this the description of the function. It will add a column to assigning a pseudo random number to each of the collection, so that all of your training features will have a random number starting from 0 to 1, and the distribution will be a normal distribution, so that you will get a random number for each of the features. So it will be useful to split the data into training as well as testing features. So now I have created my GCP. So just print the GCP. So here you will get your GCPs. So you have 382 elements. So earlier, if you can just expand before adding the random column, you have only one property in each of the feature. So here you will see you have only the band reflectances in here. So if you can just expand here, you have features, you have properties with the class number called class 1, and you also have a additional property called random, which we have assigned some of the random numbers to each of the training feature. So this will help in splitting the data into testing as well as validation features. So now let's just split this training data into two categories. So called I'm creating a variable called GCP training. So whatever my GCP is there, I want to filter it with the help of ee.filter dot less than uh, my column name, that is called random, and less than 0.7%. So whatever my 70% of the training features are there, it will go for training up of the model, and remaining 30% will go for the validation. So create one more variable called GCP testing, which is used for validation of my points. So you get GCP dot filter e dot filter dot greater than or equal to. So my random column greater than zero point 0.7 will go for the GCP testing. So now if you can just print this both of them, GCP training dot size and also print GCP testing dot size, so that you'll get what is the size of each of the feature collection. So this you can call test testing. Click on the run. So if you can just scroll it down, here you will find the number of the training features which are available for training. So out of through 382 elements, I have split it our training data into 255 and 127. So 70% for training the model and 127 for testing the model. So now let's just increase. Now let's just train our model. So if you can just come in here and paste it above after the training. Here you paste the code. So you have your GCP split into GCP training and testing features with the 255 elements for training the model and 127 for testing the model. So now I have to change some of the script here. So for the training features, here we will have to change into GCP testing, not testing, sorry, it has to be test training with the same classifier. So if you can have here, you can add one more parameter called tile scale. So this will help to increase your computation time. The larger the tile scale, the more faster will be your computation time. So I have set this parameter tile scale to 16, and you have your classifier, and you have your training features, and you have your classified band ready. So now I have used my GCP training for testing up of the features. So now I have to test the validation. So before doing that, if you can just print our classified region of interest 1 to see what does it contain. So this is our classified image. So this is our testing data set. Here you will find we have the one band with the classification as its name, and you additionally also print our GCP testing. So that we'll get what we have to compare in between the classified image and our testified image. So here you have the test GCP. If you can expand it, you have the features such as the class and random, and in a classified image you have single band called classification. So now I have to sample the regions from my uh, classified image. So create a variable called test. So for my classified image, I'm going to extract the pixel values from the GCP testing points. So with the help of simple function called sample regions, so click on the auto space for autofill. So click on the space for autofill. So you have the collection which you have to specify. So this is my GCP testing features which I have to extract the values, and the property is my class, not the random, and the scale is 10. Projection I don't want, so you can specify the tile scale to 16, and you can delete the geometries and print this. So now you print your test and click on the run. So it should be classified ROI. So here my feature collection is loading, my sample feature collection. So if you can just expand it, it has 127 elements and it has 127 features. So if you can expand the property, here you will find the class which I have given as an input is 1, and what the model has classified is classification 1. It means our model is working correctly. So for the input, it has predicted correctly. So if you can just go to other features, just expand the properties. Here you will find my class is 3, and my classification model also predicted it as 3. So most of the features has correctly worked. So let's just use some statistical measures in order to know what is the accuracy. So now I have to create a confusion matrix, so between the classification as well as the class. So if you can just go to a function called error matrix. Here you will find for feature collection we are getting the error matrix. So here you have to give two arguments which are mandatory. One is the actual class, that is whatever the training I have given, that is my class, and predicted, that is classification, so that it will generate an error matrix between what the classification has done. So let's just you remember it will return a confusion matrix. So the matrix is called as a confusion matrix. So now let's just create a variable called matrix. So for my test, that is my feature collection, so I'm having a function called error matrix between the actual value, that is my class, and the predicted value, that is my classification. That's it. Now print the matrix. So you will get an list. So it is an error matrix object. So here you will find, so ignore the first column 0 because our class starts from 1. We have classes from 1 2 3 4. So whatever you see on the diagonal, 30 36 33 38 37, so those are all out of for the class 1 we have given the 30 samples. So 30 samples has been classified as 1 only. So for the class 2 we have given 36 samples, so out of which 1 has been misclassified as class number uh, 4. So that's how you can interpret the confusion matrix. So for the class number 3, so you will find I have given 33 training inputs, but everything is in and everything has correctly classified. So this is how you can read your confusion matrix, and out of this you can generate some of the parameters such as the overall accuracy as well as the F1 score and accuracy, producer's accuracy, overall accuracy, everything can be accessed. So if you can just come to this EE.confusion matrix algorithm, so here you will find what are all the functions that you can apply to EE.confusion matrix. So you can get the accuracy, you can get the consumer's accuracy, you can get the F1 score, you can get the Kappa coefficient, you can get the producer's accuracy. So we'll print all of it. So now I have the matrix dot accuracy. So rename it as overall accuracy, and again print matrix dot consumers accuracy, rename it as consumers accuracy, and again print matrix dot producers accuracy, print matrix dot kappa, so that you can get the kappa coefficient, and again print matrix dot f score. So this is our f score, which is the average of producer accuracy and uh, consumer accuracy. So click on the run. Scroll it down. So here your confusion matrix, overall accuracy, consumer's accuracy, the producer's accuracy. So everything is loading. So here you have the Kappa coefficient 0.98. So it means that it is near to 98%. Our model has worked correctly. So here you have your F1 score to be 0.98 and your produce accuracy to be 0.97 and your consumer accuracy is also nearly 97%. Your overall accuracy is 99%. It means our classification model is working properly. So we have 99% for the accuracy of the model. So if you want to increase or decrease the accuracy of the model, you have to go for some parameters called as hyperparameter tuning, so which we will be covering in our next video. So remember to use the accuracy assessment whenever you are building a model, and make sure your model works good and well. So that's it guys for today. We have seen how you can calculate the accuracy assessment parameters such as kappa coefficient, the overall accuracy, the error matrix. So everything is covered in this video. So if you have any kind of queries or doubts, you can always post it in the comment section. Thank you for watching.